Great. Okay, so the next talk is by Alexeev, and she'll tell us about moduli spaces of principal two-group bundles. Thanks.
All right, thanks to Pavel for the introduction and to the organizers for organizing the event and for inviting me to speak. So let's start with the following data. Let's let G be a compact Lie group, and let's fix a 3 cocycle or a cohomology class alpha. And so now, depending on your background, first of all, maybe you would like to call alpha lambda. And once you've done that, maybe you've thought of different fun things that we could do with this data. So here's an incomplete list. You might like to do steady Chern-Simons theory, G equivariant elliptic cohomology, string structures, equivariant gerbs, orbifold actions on B fields, higher representation theory, and so on. So this is initial data for a lot of different areas of math. And in today's talk, we're going to focus on yet another one, which is specifically a smooth 2 group, curly G, defined from the data of G and alpha, and its moduli space of principal G bundles, 2 group bundles. And the vague expectation that kind of appears in flashes throughout the literature is that all of the above topics are related in some way to something like G bundles or the moduli space of G bundles. Of course, all of the above topics can also be hard or abstract or both, and this makes it challenging to study them individually and especially challenging to relate them to each other. And so we start by focusing on the special case where the group G is finite, where we can get a little bit more hands-on with all of the data. And in that case, we can study the moduli space of G bundles concretely and show that it has nice properties. And this allows us to make explicit connections to the above topics. And in fact, we started with the finite group G thinking it was kind of a toy model and that the case of a compact Lie group would be much, much more complicated, but we've learned a surprising amount about the general case just from this case, and we've also gotten specific ideas about where we need to modify things to general. So this talk is based on joint work with Dan Berwick-Evans, Laura Murray, Apurva Nakade, and Emma Phillips. All right, so we fixed the following input data for the entirety of the talk. We're going to start with a finite group G. Now, instead of U1, we're going to take any abelian Lie group. And alpha is a 3 cocycle, and I'm going to throw around cocycles and cocycle conditions sort of freely throughout the talk. So I thought I'd start by reminding or telling you about this. So D alpha is a 4 cochain, and it's defined as follows. So we input 4 elements G, H, K, L, and we start over here without the G, so the H, K, L, and then the G comes in at the bottom. So we have GH, and the H moves over, and then the K moves over, and the L gets bumped up. So that's how we define cocycles for any n. And this should be 1 in the group A. Okay, so that's our starting point. And now we can proceed with the talk. So here's the plan. We're going to define smooth 2 groups and discuss examples. Then we're going to define principal 2 group bundles and give our key results, which are special properties of this moduli space. And then once we've done that, we can relate back to our original list of topics, especially in the case of a finite group. And so we can relate to those, but we can also then relate between those using G bundles as a bridge. Okay, so we're going to start with definitions and examples for smooth 2 groups. And actually, we're going to start just with abstract 2 groups. So 2 group is a monoidal groupoid. So we have a category in which all morphisms are invertible, and it's got a tensor structure. And then we furthermore require that all objects have tensor inverses. And so our first baby example comes from an ordinary group, which we view as a category in a boring way with no interesting morphisms. And then we'd make it into a tensor category using the group structure. So we tensor 2 objects, H and K, and we get the object H times K. Okay. And in order to ordinarily give a monoidal category, we would need associativity morphisms and things like this, but because there are no interesting morphisms, that is all immediate. Okay, the second example is less interesting in the object sense and more interesting in the morphism sense. So we start with an abelian group and we form a category with one object, an automorphism group A. And of course, composition is given by the group operation in A. So this is the usual construction of a groupoid with one object starting from a group. But now because we started with an abelian group, we can further make this into a monoidal category. And of course, when we tensor our object with itself, we have no choice but to get that object. And when we tensor two morphisms given by elements of A, we take their product to get a new element of A, which is a morphism from point to point again. And so the reason that A needs to be an abelian group is that we have two group operations on A that are compatible. And so this is an Ekman-Hilton kind of argument. And so we get a two group again. Okay, so now we're going to actually mix those two examples and combine the data of the group G and the abelian group A using our cocycle. So we define a category whose objects again are the elements of G, but whose morphisms are elements of A. So more precisely, if G and H are not equal, there are no morphisms between them. This is a skeletal category. And if they are equal, then we have the automorphism group being A. Right, and just like we did for the ordinary group situation, we defined the tensor product using the group structure. But we now have to say something about associativity because we do have interesting morphisms. So to make this into a monoidal category, we need to specify associativity morphisms between GHK, G tensor H tensored with K, and then G tensored with the object H tensor K. But of course, this is just GHK as an element of G, and so is this. And so to specify an associativity morphism, we need to give an element of A, and we use our cocycle to do that. And so then, of course, this associativity morphism data needs to be compatible. And so it needs to satisfy the pentagon axiom. And so let me remind you what that says. So if we start with 4 elements of our group, G, H, K, L, and we start with the brackets as far to the left as they can be, we can move them as far to the right as they can be in 2 ways. And so here, for example, we treat G tensor H as one object, and we can move the brackets so that K goes from the left to the right. So we can do this going around like this, or around like this. And this is gives us the following equation, which is exactly dividing out by this, gives us our 3 cocycle condition on alpha. So alpha, a 3 cocycle is exactly the information that we need to make curly G into a monoidal category. Now, we started with a finite group G, and we got a 2 group curly G, and it was finite, which means that there are finitely many isomorphism classes of objects. And in fact, in the examples I showed you, there were finitely many objects because our categories were skeletal. And it's a theorem due to Sin, who was a student of Grothendieck in the 70s, and then later written up in more modern language by Baez and Lauda, that up to equivalence, all finite 2 groups arise in this way, meaning that we start from a finite group G, an abelian group A, and a 3 cocycle alpha. And the slight difference here, the complication, is that the abelian group A could have a G action. And so our 3 cocycle condition could change a little bit. And the definition is very similar, just is slightly more complicated. Okay. So the point of this is that by studying these specific groups defined on the previous slide, we are studying all finite 2 groups. Okay. Now, I said that curly G was combining the data of our point mod A 2 group and our ordinary group G. And let's make that more precise now. So we have a short exact sequence of 2 groups. Point mod A includes into curly G, and the quotient is the ordinary group G. And so we think of curly G as an extension of G by point mod A. And this short exact short exact sequence splits exactly when the cocycle alpha is a co-boundary. So this is very analogous to the familiar story about extensions of a group G by an abelian group A. These extensions are classified by H2, and analogously, our point mod A extensions of G are classified by H3. So just one quick comment. So if our group A has a trivial G module structure, as in my explicit example, then this is a central extension, and otherwise it's not. All right, so here's an example of this extension construction in a not finite case. So we look at H3 of the spin group for n at least equal to 5, and we know that that's isomorphic to Z, so we choose a generator and we choose a representative of that, and let's call that alpha string. And so then we can define the string 2 group as the central extension of spin n by point mod U1. And so this presentation of the string group is due to Chambre-Prise, and it's very convenient because previous constructions of the string group that didn't deal with the higher categorical stuff of the 2 group became infinite dimensional and more complicated in other ways. And so as long as we're willing to do a little bit of category theory, we have this very nice presentation of the string group. So of course we could choose the other generator, right? We could take the other generator of Z, and Chambre-Prise tells us that we get an equivalent 2 group, and the difference is that it differs by the involution of point mod U1. Okay, so I want to relate those examples. So obviously, if we're working only in the finite setting, we can't say too much about the string group, but in certain cases, our finite 2 groups are related to the string group. So let's assume that we start with a finite group G naught and an orientation preserving representation, rho naught. And then we can take spin living over SON, and we can take the pullback. So spin is, the fiber is going to be Z mod 2, and so we get G, a Z mod 2 extension of our original group G naught, and it has a map rho like this. So that's kind of our classical extension. And now we want to do the same thing with string. So string, as we saw, is a point mod U1 extension of spin. And so when we take the pullback square over here, we're going to get a 2 group, which is a point mod U1 extension of G. We've just explained that point mod U1 extensions of G are classified by 3 cocycles. And it's exactly the 3 cocycle that we get by pulling back this alpha string by this map rho here. And so many of our examples of finite 2 groups can come in this way if the 3 cocycle has this form. And those ones are related to the string group. But of course, not all 3 cocycles look like this. So this is not the whole story. This is a good class of examples. All right, so that was 2 groups, but now we want to do some more geometry, and so we want to define smooth 2 groups, and the way that we do this is we worked in the bi-category of smooth stacks and define a smooth 2 group to be a group object in there. So again, since this is a bi-category, our group axioms don't hold on the nose, they hold up to specified 2 isomorphisms, which in turn satisfy compatibility conditions. And so that's exactly the kind of thing we discussed when we looked at the pentagon axiom. So all of our above examples fit into this framework. Of course, for the finite examples that we discussed, they are discrete in terms of objects, but not necessarily in terms of morphisms. So for example, if our A is U1, then we have some geometry there. Okay, so that's the first section. We now know what the basic objects are, and now we want to have them act on stuff. So we want to define what is a principal bundle for a 2 group. So we're going to fix a smooth 2 group. For the moment, it does not need to be finite, and a smooth manifold. And our goal is to define a bi-category of principal 2 group bundles over X. Now, this is not totally new, but the thing that was confusing for us at first is that there's many different approaches, and some based on analogies with the classical setting, and others you can just cite Lurie and say infinity principal bundle. and then truncate or something like this. And so we needed to know which of these approaches was correct. And in the end, we found a favorite, but it specializes to all of the other possibilities we considered. So that's why it is our favorite. So we take a smooth stack over the base X, which is equipped with a G action, which is locally trivial. So if I hadn't written italics here, this would be totally familiar, the data of a principal G bundle. And so what does it mean to be locally trivial? There's a surjective submersion Y over X. And when we pull back P, we get a trivial G bundle. So we have an isomorphism of G stacks like this. So we want to understand this data, especially, it's a smooth stack. So what kind of objects can we get? Oh yeah, that's a good question. So what do we mean by an action? So we do mean that we should have a map. I guess it's like this. Let's call that act. This diagram should commute. That turns out to not be extra data because X is just a manifold, but we need plus. So we're going to get maps like this. And we need a 2 isomorphism between that. Does that answer your question?
Thanks.
Yeah, so of course, if I changed everything not to be italic, it would be the same words that you would say for an ordinary bundle, but this action has more content than it did before. Okay, so our first step in understanding this data is to observe that in fact we have a forgetful functor from these new objects that we just defined to bundles over the ordinary underlying group G. And so one way to think about that is this guy was locally Y cross G, curly G, and if we take isomorphisms of this stack, we get Y cross ordinary G. And so locally, isomorphism classes form a trivial G bundle and they glue together to form a G bundle. And so here is a theorem that this is a torsor over the symmetric monoidal bicategory of A gerbs on X. So we mean that the fibers of this map are non-canonically isomorphic to this bicategory, and that there's an action of this bicategory in a nice way. So the way we prove this, it uses a check style reformulation of this bicategory. And so everything is determined, is described in terms of open covers and trivializations and compatibilities between the trivializations. And then we can compare with the same kind of check data that we get for a gerb. So let me remind you or tell you how we're thinking about gerbs. So an A gerb over X for us is determined by a choice of surjective submersion and a check 2 cocycle, which we call gamma. And a 2 gerb, again, surjective submersion and a check 3 cocycle. Now, of course, an ordinary principal A bundle would be determined by, let's call it rho, a check 1 cocycle. So we've increased the category level in some sense by increasing the number of copies of Y here, and that gets us from principal bundles to gerbs and to 2 gerbs. But the other aspect of this talk, when we talk about principal curly G bundles, we're taking a higher category approach over here, and we're generalizing the group target to a 2 group. So I just wanted to clarify that we have kind of orthogonal directions of complicating our story. All right, so here I want to prove this fact that the fibers of the forgetful map from 2 group bundles to group bundles are non-canonically copies of the bicategory of gerbs. So let's just start with the data of G and alpha, and then a point downstairs. So a principal G bundle on X. And the claim is that this determines a 2 gerb on X. So one way to think about this is we associate to P the check data of a cover and row. And then we obtain a 3 cocycle by pulling back alpha. So here's the formula for a 3 cocycle. Another way to think of it is that alpha determines a 2-gerb already on point mod G, and P determines a map from X to point mod G. And so we pull back alpha along that map and we get a 2-gerb on X. Okay, now we let P be a principal G bundle in the fiber. So living over our ordinary bundle. Now we show that the data of P is actually equivalent to the data of a trivialization of this 2-gerb. So the fiber is the bicategory of trivializations of a 2-gerb. But then the bicategory of trivializations of a fixed 2-gerb is non-canonically isomorphic to the bicategory of gerbs. So there's an action of the bicategory of gerbs, and any 2 trivializations differ by a unique gerb. Okay, and so that is how we show that our fibers are this bicategory. Now I want to rephrase this in a different perspective. So maybe in a topological perspective, you might have thought that we could define our 2-group bundles in terms of classifying stacks. So let's attempt to make that definition, and let's define the classifying stack of curly G to be this homotopy pullback, where we have BG mapping to B3 of A using alpha, and then we have the cover point over B3A and we pull back. So if that's a good definition, sort of by abusive notation, this is the classifying stack. And so we expect that principal curly G bundles are classified by maps from X to BG. But this is a fiber product. So what does it mean to give a map into it? Well, we should give a map into BG and a map into the point, which are compatible. A map into the point is no data. So in other words, we need to give a map into BG and a trivialization of this composition. And translating back, that means we need to give a principal G bundle together with a trivialization of the 2-gerb. So that's exactly the story that I just told in the smooth setting. So this is consistent with our definitions as well.
There's one more question from Ezra.
Yeah, I'm concerned about this map alpha.
Yeah.
I mean, do you have an explicit presentation of a BG and an explicit presentation of the Allenberg-MacLean space B3A such that you can write down alpha explicitly, or is this only an existence that we know there is some alpha that exists?
Right, so we are not working with this definition. We are working with the other definition that I gave earlier. And so I just wanted to give a slide that said that if this was your preferred definition, if you thought of G bundles in terms of classifying stacks, that we would expect, we get the same behavior that we would expect in that story.
Well, it would be my favorite definition if I knew how to write down alpha. And I was just wondering if you did.
We did not do that in our paper.
Okay, thanks.
But it's good to know that there would be an audience for that. Okay, so another thing is that maybe you only care about flat G bundles. And since I was talking about finite groups to begin with, it's not clear that, that I should be working with all principal curly G bundles or flat G bundles. And so again, if we only work with flat G bundles, there's another definition that pops to mind. So first, let me tell you the definition that we use based on our favorite approach. So we give curly G the discrete topology, and then we define flat G bundles to be principal G delta bundles. But on the other hand, maybe your favorite fact is that flat principal G bundles are classified by homomorphisms from the fundamental group. And we prove that this definition works as well. So for a nice manifold X, flat principal G bundles are classified by homomorphisms of 2 groups. And if we want to get rid of this adjective, we haven't written the proof carefully, but it seems like what's going to happen is that you need to put a 2 group here, which is pi less than or equal to 2 of X. Okay, so let me say a few words about homomorphisms of 2 groups, just because it's kind of fun to unwind the definitions a little bit. And specifically, we want to consider the functors between the bicategories point mod pi 1 and point mod curly G. So let's look at the classical setting first. This is kind of how we do everything in this project. So we look at point mod pi1 into point mod ordinary group G. And to give a functor is equivalent to give a homomorphism from pi1 to G. But now we want to lift this functor so that it lands in point mod curly G instead of point mod G. And to lift that, we exactly need this gamma, which is a map from pi1x squared into A. And what does gamma do? It proves, maybe evinces, that rho is a homomorphism. So for every A and B, we need to provide an isomorphism between rho A, rho B, and rho AB. So that's what gamma does, and it should satisfy some compatibility cocycle-like condition, which is exactly this guy here. And this, well, the notation is suggestive with previous things that I've said. Okay. Now, what about natural transformations? So if we have two rows, which are homomorphisms in our category of functors in the classical setting, to give a natural transformation, we exactly choose a T which conjugates one to the other. And so now in the two group setting, we need to prove that it conjugates one to the other. We need to provide data that does that. And so we provide a map eta from pi1 of x to A, which gives these isomorphisms. And of course, it should also satisfy a compatibility condition like this, involving all of the input data, rho 1, gamma 1, rho 2, gamma 2. So that's the category structure. Now, this is a bicategory, but it turns out that the two morphisms are easy. There are only two morphisms between natural transformations that are actually equal. And then the automorphism group is just A again. Okay, so now we have this really nice category, bicategory, and under the conditions that X was nice in our previous theorem, we can identify these bicategories. And similarly, we have this holonomy story downstairs where flat G bundles are the same as functors, and that's the same as the action groupoid of homomorphisms by G acting on the right by conjugation. Okay, and so now when we wanted to study this map, which I said was very important, we've replaced it by this map over here, and our downstairs category has very simple morphisms. And so what we do is we show that this action of G downstairs lifts to a compatible action of G on the bicategory upstairs, and that this data is equivalent to proving, first of all, that pi is a 2 fibration and choosing a cleavage. So let me say a little bit about the action of G. So to define an action on a bicategory, we need to give autoequivalences Fg for every element of the group, and then those need to compose up to isomorphism, and those isomorphisms need to satisfy higher compatibility. And so in particular, I'm just going to talk about this functor here. And for example, on objects, we start with a rho gamma, like we just saw, and we get rho G gamma G, where rho G is just the conjugation action, just like it was downstairs. And so the map rho G sends A to G inverse rho A G. And I've inserted these brackets here. And of course, in the group G, it doesn't matter, but in curly G, it does matter. And you could make the opposite choice, but the important thing is that you're consistent. And you'll see in a second why, because gamma G, AB is supposed to be an isomorphism between rho G applied to A, rho G applied to B, and rho G applied to the product. And when we have these brackets here, we see how to give a natural definition for what rho G should be. And I'm not going to go into the whole details, but we need to move the brackets around a lot. We get the G and G inverse next to each other. We cancel those, and then we separate our rho out again. And so we get an explicit formula here for rho G, and we show that it satisfies the compatibility condition, sorry, for gamma G. So that's an action, and that's all I want to say about that. And so I want to finish by talking about connections and applications to some of these other areas that I flagged at the beginning. So let me start with a lightning introduction to the Fried-Quinn line bundle. So as before, we fix a finite group, and now we assume that A is U1, alpha is a 3 cocycle. So Chern-Simons theory for this finite setting, studied by Digraph and Witten. And then in more detail by Fried and Quinn, who construct a line bundle L, now called the Fried-Quinn line bundle, living on the moduli space of principal G bundles over Riemann surfaces. And so what does this have to do with Chern-Simons theory? Well, we fix a Riemann surface, and then we obtain a line bundle on the moduli space of G bundles on that particular surface. And Chern-Simons theory assigns to this X, assigns to X the vector space given by the global sections of this line bundle. All right, and another exciting thing about this line bundle is that if we restrict from the moduli space of principal G bundles over all Riemann surfaces to just elliptic curves, we obtain a line bundle. I'm going to call it L1, and Nora Ganter shows that this line bundle is the home of twisted G equivariant elliptic cohomology. Right, so now we're ready to relate this. So our theorem is that the two fibration pi from flat G bundles to ordinary G bundles categorifies the Fried-Quinn line bundle in the following sense. So remember that pi was a fibration whose fibers were, they should be flat gerbs, over X. Right, and isomorphism classes of these gerbs are given by H2, which is U1 over a Riemann surface. And so if we take isomorphism classes along fibers, which is a thing that we can do precisely using the technology of two fibrations and Grothendieck functors, then we obtain a principal U1 bundle on bund G. And the corresponding line bundle we claim is isomorphic to Lx. And this is an explicit computation using the fibration and the cleavage. So I also want to relate our work to string structures in the special case that G is a two group that came from the string group, as in our earlier example. So thanks to Schomer-Priess's nice presentation of string N as a two group, we can make the following definitions. So let me start with a spin structure. So if we start with an oriented vector bundle downstairs with structure group G0, then we define a spin structure on this thing to be a lift to a G bundle P. And similarly, we define a string structure on P, not sure why there's so many N's around, as a lift to a G bundle curly P. However, so these seem like very natural definitions, but before we had access to Schomer-Priess's convenient constructions, it was very hard to formulate in that simple way. And so other people had different approaches to the data of a string structure, and I want to compare it to a few of those. So firstly, let's start with the principal spin G bundle. And Waldorf tells us and defines a string structure on P to be a choice of trivialization of the two gerb lambda P determined by P and the 3 cocycle alpha. Okay. So this definition was around, and Schomer-Priess's definition has been around for 10 years. But now with our theorem, it's very clear that these two definitions of string structures coincide, because a string structure over P is exactly an element of the fiber over P, and that fiber was equivalent to the bicategory of trivializations of the two gerb lambda P. So we can see that Waldorf, even without having this concrete description of string N, had exactly the correct information. Another approach to string structures is due to Stolz and Teichner. So in the case of a flat G bundle, we consider Chern-Simons theory for P. And Stolz-Teichner define a geometric string structure on P to be a trivialization of Chern-Simons theory. So I'm not going to get into all the details, but in particular, for a suitable map from a two manifold into X, the base of our bundle, Chern-Simons theory assigns a line. And if it's been trivialized, we should have a section. So we should have a non-zero point in that line. Right? But we've proven that this line, so these are This is the fiber of the freed Quinn line bundle. And we've proven that that's an isomorphism class of a flat G bundle over the pullback star P. And so to provide a compatible family for every M2 of a flat curly G bundle, we choose a flat lift of P and pull that back. So certainly a flat lift, a lift of P to a flat curly G bundle definitely gives this data, so the trivialization for two-dimensional manifolds. Now, of course, there's more data. So with our result, we were able to compare part of the data of the trivialization of Chern-Simons to part of the data of P. So here we had the two-dimensional data, and here we had the isomorphism class of this object in a bi-category. And so obviously the next question that we want to understand is how do we compare the rest of the data, so trivialization of Chern-Simons for all dimensions, to all of the structure that we lost when we truncated our bi-category, when we decategorified to produce freed Quinn. Right, so that is all that I would like to say. So thank you, everyone.
Thanks for the nice talk. Are there any questions?
I have a quick one. Probably your first theorem, I think I have your slide here. You describe a two bundle over band G being your band curly G extension. So I wonder if you could replace band G by some factorizing version, sort of like,
oh, like a graph.
I wonder if you can extend Benson and Drinfeld's GM bundle over div X. So even for G being U1, this would be interesting.
Yeah.
If you have a two-gerb factoring over div X.
Right. Well, so far we've only done the finite case. Yeah, we haven't thought about that at all, but that's really interesting.
Thanks.
Okay, any other questions?
I would like to ask a question.
Go ahead.
Have you thought about how you could define connections in general to bundles? Because there are some things in the literature, but it's not always clear what a connection to bundle should be. And since you have thought about simple ways of presenting this.
Right, so we've studied the flat G bundles. So this gives an approach.
Yeah, but well, I mean, general connections.
Yeah, no, we haven't thought beyond that.
Yeah, okay. Okay, thank you.
Any other questions? All right, let's then thank Emily again. And the next talk will begin on the hour.